Hello everyone. Now I'm going to talk about the applications of Newton's laws. This is chapter 3 in your book. We're not going to move into harder questions yet, so we'll be hanging around chapter 2. In class we'll be solving more questions, but slowly we'll be moving into the applications of Newton's law. Now that we learned about all the forces we needed, we can safely, easily use them, solve more questions, applying them to different situations, real life situations. So let's now start the applications of Newton's law. What have we been doing so far was actually using these applications without knowing the situation in all details. What we will be doing will be the same, only we'll be moving into more complicated situations and we'll be knowing what we are doing better. So we will be using Newton's laws, first, second, and third laws, looking at situations, again, different situations. The first one we're going to discuss is equilibrium. How do we deal with a situation wherein there are more than one forces? We dealt with some simple situations. We'll be moving into more complicated situations. What is an equilibrium is that if there is a total force acting on an object 0, so if F total or if net is 0, total F is 0, since total F is equal to M total times A will be 0 for this system. So whenever we talk about equilibrium, it means total force acting on the system is 0, thus the acceleration of the system is 0. Now if a system is in equilibrium, acceleration is 0 for sure, and when acceleration is 0, a system could be moving in a constant velocity or stationary. Don't assume that if a system is in equilibrium, it will be stationary. Not always the case. It could be at constant velocity. So either v is 0 meters per second or v is a constant value. This perfectly agrees with what we learn in kinematics. If we have a constant velocity, acceleration is 0, because the very definition of acceleration is that the change of velocity in unit time. So we are here, whenever we see a system, and they told us that the system is in equilibrium, we will automatically know the acceleration is 0, total force acting on the system is 0, and we'll move on to solve our problems. The second situation will be non-equilibrium. As you can guess, in this case, the acceleration will not be 0. The system will be accelerating or decelerating, moving with an acceleration if it is in non-equilibrium, which tells us that the total force on the system will not be 0. And thus, acceleration of the system is not 0. What we will be doing is to find the total force, which is important, find the acceleration, and answer any question that is asked related to. There could be kinematics question following up. There could be only questions asking us force in a system when there are multiple forces. We'll be looking at some questions now to understand this. But the general idea is very simple. There's either equilibrium or non-equilibrium. If a system is in equilibrium, either the stationary or moving with a constant velocity, and in both cases acceleration is 0, total force acting on the system is 0. If it's in non-equilibrium, there's an acceleration or deceleration, and total force acting on the system is not 0. We already solved some questions when there were more than one forces. Let me remind you from learning catalytics. We had an object, for example, acted by F1, F2, and we looked at this situation, found that the object mass was moving to the right, it had an acceleration. This was actually a non-equilibrium situation. We had an object moving, there's a net force, total force that is not zero, right? F total here was not zero. So we had an acceleration that was not zero. But we will be dealing in more complicated situations. Let me delete these and look at some examples. Let me see what I have in here. Okay, there is a nice simple question here. Somebody is mowing his lawn. So he's pushing his lawnmower. Let me try to make a handle of a lawnmower. I'm a terrible picture drawer, but yes. So the question says there is a force acting on by the person on the lawnmower F with an angle at horizontal that is 35 degrees. And let me read you the question. This is all we have on the figure. A person pushes a 20 kilogram lawn mower. So the lawn mower's mass is 20 kilogram. Important, F is equal to ma. At a constant speed with a force of 100 newtons. So the speed is constant. Right away I got my information, the speed is constant, acceleration is 0 meters per second squared. So this system is in equilibrium. It is indirectly told me by the velocity being constant. I got that, I wrote it down, A0. So the total force acting on this system, this object, lawnmower will be 0. And this will help me to solve my question, solve everything I need. With a force that is equal to 100 newtons, so the value of force is also given as 100 newtons. And these are all the information. So a person is pushing lawnmower with a constant speed, which means 0 acceleration, equilibrium, with 100 Newton force acted on the lawnmower at a 35-degree angle with horizontal. And the lawnmower's mass is 20 kilograms. I've got all the information I need. Draw a free body diagram showing all forces acting on the lawnmower. Now this information will help me to draw all the forces acting on the lawnmower. So there is, let me draw the lawn as well. Oh, this should be green, maybe green. Yes, that's fine. So we have green grass in here, and we are cutting it, moving it. So what we have first of all is mg, right? The weight of the object. I told you in the previous video it will drop weight W. It's W anywhere, everywhere, whenever you see it, and they will show. This is equal to mass times the acceleration of the gravity, mg. So I'll stick with this. Downward, we always have mg. Do reaction forces. This object is pushing downward, right? So there will be a net force and normal force acting in the opposite direction and perpendicular to the surface. Let me use black for that. So we have normal force, and I don't know what it is at the end because it is always equal to the total forces acting perpendicular to the surface. I will have some other forces pushing down in here. If I look at F, it's pushing to the right. So it has an X component here pushing to the right, and this force is actually given the lawnmower in action, given it a velocity, constant velocity to the right. And Y component, let me draw that as well, Fy. Fy is also pushing down. Is there any other forces? If I was in the class, I would ask you and wait for this. There must be other forces. There must be one more force. Since this object is moving with constant velocity, then the only force I see here pushing it to the right, if this was the only force, it should be accelerating. That means, if it's not accelerating, that means there is a force opposite direction, which is actually frictional force. I'll call this F, and it will be kinetic frictional force. As I've told you in the previous lecture, we won't be really dealing with static frictional force. We will know it is there. There are some conceptual questions to understand it better, but generally, if an object is moving, we have kinetic frictional force. This kinetic frictional force is working against the effects. They're in opposite direction. Let us choose our direction, positive direction as well. Since the object is moving to the right, we choose it in positive direction. Here, the total force, we were going to choose the direction of total force always positive, but the total force is 0 here. Why? Because we have equilibrium. Let me write that down too. I should have written that down at the beginning actually. F total is equal to 0 because acceleration is 0, velocity is constant. So these are all the forces we have. We're done with A. This is my free body diagram. I have mg downward, I have Fy pushing downward, there will be a normal force upward on the floor, on the grass. There's Fx pushing to the right, which I have chosen to be my positive direction of motion, and Fk, kinetic frictional force pushing towards left. Done with A, let's move on to B. I'm going to solve B in here. Let's see what it is asking us. So A, free body diagram, let me put here so you'll remember. Finding all the forces acting on an object is free body diagram simply. B, calculate the horizontal retarding force on the movement. The force of friction on the ground actually is the horizontal retarding force. There must be a force, retarding force against the effect, as I've said, because the object is not accelerating. If there was not any, it would be accelerating. Now, if the system is in equilibrium, I have to look at component-wise because I have x and y directions. If my total F is 0, I am going to directly write down then total Fx must be 0, and total Fy must be 0. So for these questions, we'll be dividing system into two, Fx, horizontal direction forces, and Fy, vertical direction forces. Now, if I am looking at the retarding force along x direction, I'll be looking at only along x to solve this B, part B. That's what I need. So let's look at him here. Using the fact that total Fx should be 0 because this is equal to M total A, and A is 0, so this is 0. I know this information, I keep repeating so you will understand it better. Let me look at my forces along x. I have Fx, and I'm putting now vectorial addition first. Then Fx plus Fk, kinetic frictional force, vectorial addition should be 0 along x. Now I am moving into the directions. The choice of positive is to the right for me. So Fk is going to be negative and Fx is going to be positive. Now I am going to put their magnitudes. Fx will be positive F times cosine 35. And Fk, I don't know, to the left, and it will be negative. And these are equal to 0. What this gives me actually, Fx, or F cosine 35, taking Fk to the other side will be positive, is equal to Fk. So once I find the x component of my force, of the force that the person is exerted on the lawnmower, this will be equal to the frictional force. Why? Because the system is in equilibrium, total forces along x is 0. Let's find Fx actually somewhere. It's a different color. So Fx is equal to F cosine 35. 100 times cosine, Newton times cosine 35. The answer must be, let me get it from here, 81.92 Newton. So 81.92 Newton. Go ahead and practice this, solve it yourself, If you solve a question yourself, although it's in here, it will help you understand the situation better. Writing down notes, solving the problems yourself is very, very important for physics. So we got this. The frictional force is equal to Fx because the system is in equilibrium. Total forces along x and y are 0. So this is an equilibrium question. There is a part C. Let's go into that too. Okay, I am gonna delete this one and I'm gonna solve C in here as well. So C is asking us, probably you've guessed already, calculate the vertical normal force acting on the lawnmower. So C is simply asking us what is N equal to? Normal force. And the information I'm going to use is the same. System is in equilibrium, total Fx is 0, total Fy is 0. N is along y, so I'm only looking at y direction now to find my N. So I'm using the fact that total Fy is equal to 0. Here, let's choose the up direction to be positive. It's completely up to me. And down direction to be negative, like in general xy coordinates. So the forces upward will be positive, forces downward will be negative. This is my choice, and even if I switched them, the result wouldn't change. I would get the same answer. So the total Fy is equal to 0 will give me, I'm doing vectorial addition now, N plus Fy plus mg, all the vertical forces. I have mg down, Fy down, and upward. And their directions, N is positive, Fy is negative, and mg is negative. Our addition of these forces, vectorial addition, is equal to 0. Now when I'm entering the magnitude, moving into magnitude addition, I have to take positivity, negativity into account, so I'll get correct answer. My N is positive and I don't know what it is, so I put it in here. Let me stick with the color, the same color. My mg is negative, so it's minus mg. My Fy is negative, minus Fy, and all these are equal to 0. Since I'm trying to find N, I'm going to leave it alone in here. I'll take these two to the other side, and they go as positive. So I'll find N is equal to mg weight plus Fy. After I got that, the rest is easy. Mg, I'll find Fy, F sine 35, and I'll get my answer. Let me delete this from here. Maybe I'll leave this up to you to find mg and Fy, and I'll just give you the answer. It's 253.36. I prefer to generally add up to 2 decimals in my questions. Probably you've noticed already, but I accept the rounding, so 36 could be rounded up to 44. So 253.4 is also a correct answer. This is what we do in equilibrium and non-equilibrium questions. If you have any questions, again, please email me or post your questions online. Let's do this. I don't want to make a very large lecture of that, but I want to solve some problems today. And in the next lecture, I'll be continuing solving more problems, dealing with different situations from real life. So the 20 minutes. I have a very nice application of this that I asked you some questions in pre-lectures. But before that, let me see if we can solve a non-equilibrium question. Constant speed. Okay, let's solve this one. Now the object will be accelerated in this example. We'll have a non-Euclidean question. Process to move on is very similar. Only instead of 0 now, we'll have some values for x and y component of total mass, total forces. So let me draw this figure. So we have a boat, super tanker, whatever that is actually. This is my horizontal axis, and the forces acted on it. Two boats are pulling this object. One with T1 in this direction. As you can hopefully remember if you watched the previous video, generally if there are ropes, the tension on the rope is called T. So they have ropes and tension, so we call them T1 and T2 in these directions. They have angles 30 degree and 30 degree. Okay. We have also a P force. Let me draw that as well. Along horizontal. And then there is a resistive force in opposite direction from the water called R. So we have 4 forces in here. And the object is accelerated by A to the right. So the total force along horizontal is to the right. Since the object is not moving in this direction, then total force along vertical will be 0. Let me read the question first. A super tanker of mass 1.5 times 10 to 8 kilograms. So the mass of this object 1.5 times 10 to 8 kilogram is being towed by 2 tugboats, as in figure. The tanker's engines produce a forward drive force with a magnitude of 7.5 times 10 to 4 Newton. This is this force P. So the object pushes itself, the tanker pushes itself with a P force that is equal to forward drive force 7.5 times 10 to 4 Newton, very large force. And water applies an opposing force R with a magnitude of 4 times 10 to 3 Newton. So the opposing force by the water is equal to 4 times, let me check that again, 10 to 3 Newton. We have large forces in here. These are real applicable force to life actually. The tanker is accelerated with an acceleration 2 times 10 to minus 3 meters per second squared. So this is equal to 2 times 10 to minus 3 meters per second squared. So 0.002 meters per second squared. We can write it in this way. Find the magnitudes of T1 and T2. Actually, I'm going to simplify this question a little bit more for you. I'm going to give you one value and ask you the other one. Well, actually, we can go. Yeah, let's go as is because it teaches us something more. So it's asking us T1 and T2. There are 2 unknowns, it seems actually, but we can find an important information using the fact that along vertical, total force is 0. Let me take this as one vertical and this is a horizontal axis. Since the system is not moving along Y, let me put it to a corner so you always see it. No motion along Y tells me that total Fy is equal to 0. The fact that there is a motion along x, total Fx is not equal to 0, and along x we have an acceleration that is not equal to 0. To deal with the x motion, we say total Fx is equal to m total times a, and so for everything we needed. Along y, the total Fy is 0 gives us the fact that along y we have, let me try blue in here, green is not really visible, but let's see. T1 has a y component upward direction, T1y, and T2 has a y component downward direction. The total force along y, 0, tells me that the forces upward direction, total force upward direction are equal to total forces downward direction. So the fact that total Fy 0 tells me that T1y is equal to T2y. Let me put these here. T1y is equal to T1 sine 30, and T2y is equal to T2 sine 30. So sine 30, these two are equal to each other. Sine 30 cancels, and I got information that T1 is equal to T2. Let me call this T. And the reason why I decided that if the system is in equilibrium, the total forces upward directions are equal to the total forces downward directions, because total Fy is 0, I will be adding all the forces upwards plus the downwards vectorially, and I'll get 0. So this means the upward forces plus forces should be equal to minus forces, and this is always the case. The step up to so as not to go all the steps, we can directly now say, from now on, say, if the system is in equilibrium, total forces in one direction, upward, let's say, are equal to total forces in downward directions. Here we have only 2 forces, but we could have more. And the same goes for x, along x actually. If the system is in equilibrium along x as well, there is no acceleration, total forces to the right is equal to total forces to the left. This helps us to jump over here and directly write this equation and find the answer. I hope you can see that. So T1 is equal to T2. Now I'm going to call them as T and solve my x direction. These are equal. I got that information. Now I am trying to find what they are. They are equal to each other, but what they are as a Newton. Now I'm going into x direction. Using the fact that total Fx is equal to m total times a, I'm going to find what I need. Let's look at total Fx. The system is moving to the right. I'm choosing right to be positive and left to be negative. And I am writing all my forces. We have P in here. T1, T2 will have components. I'm going to call them T from now on. And they will have all x components along there. Let me try green again. It's alright, I guess. So we have here T1x plus T2x, right? Since T1 is equal to T2, they are equal to each other. T1x is equal to T2x. Let me call them Tx. And they will be equal to T times cosine 30, right? They are to the right. I have P to the right direction, positive direction of my choice, and to the left I have R. So when I write total Fx, let me not skip this, or should we? Let's skip this. Take the forces to the right minus forces to the left, which is what we're going to get. This is vectorial addition again, but I'm just giving the step of showing them vectorial addition. And I'm going into magnitudes. The total force to the right, positive forces are T1x plus T2x plus P to the right, minus force to the left only is R. And this is equal to m times a. M total is only m, the mass of this object, supertanker. And this will get me to the answer. Let's find T cosine theta here. Oh, we won't find it. Sorry. we'll have to leave it as cosine theta because what we're trying to find is t, not t. So let's put the values. T cosine theta, t1x, plus t cosine theta again, t2x, plus p, we know this as a number. Don't fit in here, let me not put the numbers in. Plus p minus r is equal to m times a. 2 times t times cosine 30 plus p minus r is equal to m times a. Now delete some parts and carry this somewhere to solve. What I am solving for is t. I know cosine 30, I know p, and I know r, I know m, and I know a. I can solve for t now. Let me delete this part maybe and carry it there. Not gonna be enough. I have too small board, not good. Alright, let's go. I'm solving for t, so 2 times t cosine 30 is equal to ma. Minus comes out as plus to the other side, so plus r minus p. And t is equal to divide each side by 2 cosine 30, ma plus r minus p divided by 2 cosine 30. And this is my t. Go ahead and enter all these values there. I can also do it for you. I have the answer already. Okay, let me do this part and put the numbers. And please do this yourself as well. So t is equal to, I'm entering all the values. M times 8. M is equal to 1.5 times 10 to 8 kilogram times a 0.002 meters per second squared, or 2 times 10 to minus 3 meters per second squared. I'll put in parentheses so it will be clear. R is equal to 4 times 10 to 3 Newton. So plus R, 4 times 10 to 3 Newton, minus P, the push force that the supertank has from its motor, 7.5 times 10 to 4 Newton, divided by 2 cosine 30. Once you enter all these values, you'll get T as, let me see what I have here. 1.53 times 10 to 5 Newton. This is the forces acted on the ropes by the 2 boats that are pulling the super tank. Please solve the question and check the answer to make sure I'm right. If not, let me know. So this is a non-equilibrium question. Non-equilibrium along x, so Fx is equal to m total times a. Along y there is no motion, so along y we have equilibrium. We use that fact to find some information about the forces. Alright, it's 30 minutes already. The last thing I want to talk about now is you have some conceptual questions about this on your pre-lecture quiz. It's quite intuitive. We do this almost every day, so you felt what happens already probably, but it's a very, very nice way of looking at applications of Newton's laws, equilibrium and non-equilibrium. So what happens to a person in an elevator? That's what we're going to discuss, and that will be the end of this lecture. I'm going to give you some examples, and I'm going to let you decide what happens. I'm also going to put some questions on learning catalysts, so we will be still practicing these. So a person in an elevator. Let me use red. To decide how your weight changes in an elevator, what we're going to use is equilibrium and non-equilibrium. So let's put our equations. Total force is equal to 0. Gives us that A is equal to 0. Equilibrium. If an object is stationary or moving with a constant speed, we have equilibrium. Total force is not equal to 0. The all total force is acted on an object. Let me put vectors if it's not correct. Then A is not equal to 0 because total force is still equal to MA. System is in non-equilibrium. So when we're dealing with the system, we look at total force is equal to MA to, let's look at that. So A is not equal to 0. Now, as discussed in the person in an elevator, we'll be looking at equilibrium, non-equilibrium situations. If you ever notice, probably you did, when we get on an elevator, once the elevator starts moving up, let's say, we feel a force pushing down. At that moment, if you happen to have a scale under your feet, your weight will be larger. And as it moves on up, goes, once it almost reached to your floor, it starts slowing down. Once the elevator starts slowing down, you're pushed up a little bit. You feel like your weight is lighter. And it is lighter. If you happen to have a scale under your feet, you will see that your weight is lighter. And these are all applications of Newton's laws. To find how your weight is changing, you use Newton's laws, equilibrium, non-equilibrium. That's it. So a person in an elevator, let's look at the first situation. An elevator moving with a constant speed. This is we also feel. Let's say we're going up again. At the beginning, we feel that force pushing up downward at the beginning for a short time, and then we feel okay. Elevator is going up. This is constant speed. There's no acceleration. Until it starts slowing down with an acceleration, then we will feel the force pushing us up. So if you are ever asked to find what is your weight in an elevator, let's see there is an object. Say there's a person in here and testing this application. He or she put a scale under his feet and testing to see if his weight is changing or how his weight is changing. Once you get a question about this, the force that the scale read is a normal force, total normal force acting on the scale. We always have mg downward, so let me show that the weight of the person. And the weight of the person, mg, will change depending on the motion of the elevator. This is n, this is what the scale if this elevator is going up or down, doesn't matter. If the velocity is constant, A is 0. So total force acting on this object is 0. Let's say the elevator was going up. It's optional again. Then choose up direction to be positive. If the up direction was positive, V is constant, A is 0. Using the fact that total F is equal to 0, because it's equal to MA and A is 0, total force will be addition, vectorial addition of these two forces. Again, I'm going to skip this vector part. We'll be adding the magnitudes. When we're adding the magnitudes, we're going to be looking at positive and negative direction. So N is positive, minus mg is negative in here. So the total force is equal to N, positive, minus mg. This is equal to 0. So what this tells me is that N is equal to mg. So if the elevator is going up or down, doesn't matter. The scale will be reading your normal weight, mg. And N again is what scale is reading. You'll get some questions about these. Constant speed, 0 acceleration, equilibrium. Now let's look at an equilibrium position. Let me put it in here, then I'll delete the equilibrium one. So 2, I'm moving to the opposite direction, to the left. Let's say the elevator is accelerating upward. direction. System is in a non-equilibrium, not in equilibrium. There's a net force, non-zero. So let me draw my elevator again. I'll draw it a little smaller so we'll have some space here. The person is here and he's trying to see what his weight is. The elevator is accelerating upward, so I have an acceleration in this direction. Motion is in this direction. If I have an acceleration in one direction, the total force will be in that direction as well. So F net or F total is also in this direction. And what would the scale read now? It's again N, it will be reading N, but M will not be the same now. So normal force is again what the scale is reading, and the system is not in equilibrium. Total F is equal to M times A, M being the mass of this person. M times A now, not zero. Since the object is moving upward, accelerating, let's choose upward direction to be positive, direction of motion, and the total force. As we've decided at the beginning, to choose the direction of total force, if there is one, if it's not zero, to be positive. So let's choose it in here. Here the total force was zero, so I choose an arbitrary direction to be the direction of motion. But if I have a total force, I know which direction it is, I will choose the positive direction to be that. Please my work. Again and again I keep saying this is optional. If you change the direction, as long as you you stick with the positive negatives and don't confuse yourself, you'll be finding the correct answer. So upward direction positive, so my N will be positive, or my mg will be negative again, and the total force is equal to ma. So let's put these in here. When I'm applying total force, again I'm skipping the vector part, I'm moving to magnitude part, I'm putting plus and minus values. So N is plus, minus mg is equal ma. Now if I solve for N, what my scale is reading will be ma plus mg. Mg goes to the other side as positive. So I look like I have larger weight now when the elevator is accelerating upward. And we felt this push many times. I'm sure you are all aware of that. And this is the reason Newton's laws. So next time you can teach it to someone in an elevator. Smart. I'm going to look at one more situation, so it is 40 minutes, and I am going to put a post on Twitter for you to discuss with me other situations in elevator and tell me how your math would change. And you also have a conceptual question, one or two, in your pre-lecture for tomorrow. So 3, an elevator is let's do one deceleration. Decelerating, and I'll ask you the rest. Let's say upward, okay. Should we choose downward, upward? Let's choose upward. I'll ask you the downward ones. So now our elevator is not accelerating, going upward, but decelerating. So the person is here, he's looking at his scale, mg here, and is again what the weight scale reads. M is the mass of the person. The elevator is going upward, the motion is in this direction, but it's decelerating. If you can remember from the kinematics part, if an object is decelerating, acceleration is against the motion. So A will be down in here, in down direction. If A is down direction, A is always in the same direction as a total force. So total force is here in down direction. F total, let's call this. And here, I always want to choose the total force direction to be my positive direction in this section. So I'm choosing downward direction to be positive in this case, and upward direction to be negative. And I'm applying my Newton's law. Total force is equal to ma, and it's not zero, I have a deceleration. Now let's write down total forces acting on the scale. Downward I have mg, I choose downward direction to be positive, so it's now positive. upward I have n, and it's now negative. Now I am again skipping the vector part. I am applying magnitudes, and I'm taking magnitudes as positive, negative. I have decided the directions already, and I am good. So downward mg minus n in minus direction is equal to f total ma. My f total is also plus, because I always choose this direction to be plus, right? If you change the directions, you have to know what you're doing. I would suggest you not to change. Always take the direction of f total to be positive, so you won't be having mistakes. Okay, so mg minus n now is equal to ma. If I rearrange this for n, I'll get n is equal to mg minus ma. So you're lighter, and you feel that already. Go and retry this, feel this, if you haven't noticed this before. I'm sure you've noticed, but that's what happens. So your weight is less because the acceleration is, the elevator is slowing downward. Accelerating, yes, downward. Now I'm gonna ask you on Twitter to discuss what happens if an elevator is accelerating downward and decelerating upward, and show me what happens there as a bonus mark. And you'll have some questions in class and learning catalytics next week probably. So see you in class.